Hello? Okay. Is that good? Okay. All right. Hi, everyone. I'm Maddy, and today I'm going to be talking about some joint work with Alex Lev, Armando Solar-Lezama, or sorry, Josh Tenenbaum, Vikash. Wow. Okay. Sorry, thrown off by the AB things, but some joint work with Alex Lev, Josh Tenenbaum, Armando Solar-Lezama, and Vikash Mansinghka. So this is going to be a talk about the value of laziness in inference. And this is actually something that was realized very early in PPL literature, going back to the stochastic Lisp of Daphne Koller and colleagues in 1997. But it's something that's been largely abandoned in the past decade or so as we've developed very modern, sophisticated inference techniques. And so first, let me tell you a bit about why laziness has been long recognized as useful for inference. So say we have a probabilistic program like perturb that we've written, called perturb, that takes a string and it's going to introduce some typos into that string by randomly inserting and deleting characters. So if we run perturb a few times on our input, like the word lazy, we're going to get a range of different corrupted strings. And just to break down the code for this program a bit, it's going to start with a helper function that takes a string and inserts any number of characters. It also has this function maybe keep that's going to decide whether to drop a character. And finally, the actual implementation of perturb is going to, if the string is nil, just insert any number of characters. And if the string is a cons, it'll decide whether to keep that first character, insert any number of characters after it, and then recurse. So in essence, this is walking along the string, deciding whether to drop characters, and also at each point inserting any number of characters. And a natural question about a program like this is, say, what is the probability that we corrupt our input string to some particular output, like the string lucky? So one approach to this is going to be to enumerate all the possible executions of the program. Right? So for example, at the first step, we could decide to keep that first letter and insert a U and a C after and get this prefix luck. And here I'm showing the completed prefix in this bold green and then the recursive call in red. The remaining recursive call, which might add additional characters. Now, another option is we could drop that first L and say insert the whole word luck. Or we could say drop the first L and insert literally any prefix. So for example, DEN. And if we continue this process and unroll this recursion, we end up at the bottom with this tree, or at the bottom of this big tree of execution paths, we end up with all these concrete corrupted strings. And if we add up the probabilities of the paths that lead to our target string, lucky, then we've solved their problem. But the problem with this is a really big tree. In fact, it's infinite. And it's even infinite at the very first level, because we can insert a string of any length through this recursive maybe insert function. So standard enumeration is never going to terminate. But what if we adopt a lazy semantics for the program? So when we want to evaluate the lazy expression equals of perturb lazy to lucky, we're going to thunk perturb lazy, right? We thunk our arguments. And then the implementation of equality is going to have its usual implementation that is going to run perturb just enough to figure out the possibilities for that very first character. And importantly, it's only going to actually recurse on the rest of the string if that first character matches. And this ends up making a huge difference in this case. So it brings us from this infinite tree to actually a finite tree, where essentially we no longer explore any of the paths that involve a prefix that doesn't match, that isn't a prefix of our actual output. And another way of thinking about what's happening here is that we're essentially laziness by not evaluating choices that are in thunks that don't get forced. It's implicitly marginalizing over all of those choices in the unforced thunks. Now, that said, there's still an exponentially large tree here. And it's exponential because there's a lot of work that's being redone at each step. Or rather, there are many paths that lead to the same intermediate state. And modern techniques for inference are going to exploit independent structure in the program to avoid this, avoid redoing work here, and essentially bring us from exponential time in the length of the string to polynomial. So this talk is going to be about how to combine modern inference techniques that do that kind of, that use independence in that way with laziness. So in particular, we're going to focus on a technique called knowledge compilation. Knowledge compilation is a state-of-the-art technique for inference in discrete probabilistic programs. And at a high level, what it does is it compositionally translates some input probabilistic program to a representation of all of the paths through that program. And importantly, this representation is a graph instead of a tree, so it can capture how multiple of these paths actually lead to the same intermediate state. So this allows it to capture exactly that sort of sharing that we wanted in the perturb example. But the issue here is that standard knowledge compilation is strict. So for example, when compiling an expression like x equals E1 and E2, we're first going to compile E1, then compile E2, and then we're going to use these two to construct our result. And E1 ends up getting compiled whether or not it actually used an E2, which ends up on programs like perturb, meaning that we fail to terminate for the same reasons as strict enumeration. So how do we make knowledge compilation lazy? Now, in this talk, I can't give a full overview of our algorithm, but I wanted to point out a couple of the key ideas of it. So one component of our approach is that we're going to delay the computation of sub-expressions until they're actually forced, much like in normal lazy evaluation. So for example, with let x equals E1 and E2, we're simply going to thunk E1, and then we'll go ahead and evaluate E2 only forcing E1 in the case where E2 actually uses it. And we're similarly going to use thunks for compiling function calls and constructor applications for data types like lists or trees. So this ability to partially compile expressions of list types turns out to be useful, but it's actually not enough alone to get the full benefit of laziness. So to see why this is, let's look at a simpler example than perturb. If, for example, we have this program that in its first step generates a random list of Booleans with random length, and then in the second step, evaluates whether all of these Booleans are true. Now, note that so far, if we're doing a lazy evaluator, if we tried to, at this point, just evaluate B, there are going to be infinitely many ways to get there, because there are infinitely many random lists of Booleans that we can create. But if instead we had an expression like this, where the last line of the program only evaluates B if the length of x is, say, less than 4, then the lazy semantics is going to have a finite set of execution paths that lead to these short lists. But how can we actually capture this in the knowledge compilation? Because if we just thunk x's and thunk b, and then evaluate our thunks when we get to this b call in the branch, then, and we just do classic knowledge compilation, we're going to end up compiling that whole big infinite representation for all of the paths, including the ones involving longer lists. So the key here is we can use this path condition that length x's is less than 4. So by the time we actually force this thunk in a branch, we don't need to compile a representation of the whole distribution of V. We can just compile the part that is consistent with the current path condition. So this generally is a key benefit of this lazy compilation approach. We get to compile the conditional distribution of a thunk given its path condition, which can often be dramatically smaller than the full distribution of the thunk. In this case, bringing it from infinite to finite. Yeah. And this can make knowledge compilation much faster, even on examples where standard knowledge compilation does terminate. So, for example, there are lots of programs with this kind of high-level structure, where we have x's coming from some distribution, and then we're asserting that we're observing that x's is equal to some concrete list of values. And because each element of x's is only forced if all of the previous elements equal their observations, we can actually just represent these conditional distributions of the next element given all the previous ones were the observed values. So for example, on the distribution of the third element, we can basically evaluate the conditional distribution that the third element is 6, given that we already know that the first two are 1 and 3. Now, that was just a high-level view of some of the benefits of lazy knowledge compilation, and there's a lot more that we're happy to chat about at the poster. But let's talk about what this buys us empirically. So we've implemented this approach in Julia and compared it to both enumerative approaches and standard knowledge compilation on a range of benchmarks. So first off, on the DICE benchmarks, a lot of these, these Bayes nets and network reachability problems don't really exercise the kind of data structures where laziness really pays off. So generally, we either do better on some or worse on some, depending on overheads of the laziness. But then additionally, we evaluate on these more structured distributions. So in particular, we have a Markov model, a PCFG distribution, that perturb example, a more complex version of it, and sorted list generation, sorted list generation problem. And with all of these, we end up running in a matter of milliseconds instead of seconds or minutes, because we can just represent those conditional distributions. Right. Oh, and I should mention, right, HMM is actually, I suppose, a special case because that's one where there's DICE can still run fast because of the independent structure in the HMM, but for all of the other examples, there's a dramatic effect from using laziness. Now, if we vary the output sizes on these examples, we see that laziness allows for polynomial scaling, while DICE scales exponentially. And additionally, for all of these examples, we've been giving DICE a recursion bound, and we've been setting it just low enough that DICE produces the right answer. But if that bound is set too low, you get a wrong answer. And if it's set too high, runtime scales exponentially, even for a fixed output size. So that's another place where laziness pays off and effectively kind of infers the right bound for your recursion. And finally, there are two other evaluations we did, which I'm happy to chat about at the poster later. One on randomly sampled programs from a range of grammars, and one where we put our program in the loop of MCMC-based probabilistic program synthesis. And so in summary, we've revisited this classic idea that laziness implicitly marginalizes over irrelevant choices. We've adapted a modern knowledge compilation method to benefit from it. And there's lots we didn't cover, so please come by the poster if you're interested in chatting about things like how we actually do knowledge compilation here, how we handle cache validity with laziness. There's fuzzing and synthesis evaluations, a programmable approximate inference version of our algorithm, actual formalization of this in terms of the lazy PPL semantics of dash et al., or anything else that you're wondering about. Thank you.
Thanks very much, Maddy. I think we have a moment for questions while Jack comes to set up.
Hi, thanks for the talk. I think I missed one detail is in one of your examples, you have an observation and you say if the observation doesn't match, you cannot evaluate the rest. But how do you compute the normalizing constant if you don't evaluate all the branches?
Let's see, how do you compute the normalized? So if the, let's see, I think we don't, well, right, we're summing over actually all of the paths, so we don't need to compute a normalizing constant for the, yeah, well, we can also just check offline at the poster if that's good. Sorry.